So now we are going to be on the almost last topic for this semester, and that is electrochemistry. So this is one of three presentations that we're going to work on. So the first thing that we want to talk about in electrochemistry is what we call voltaic cells. Voltaic cells are spontaneous redox reactions, and these are what we use for a source of energy. So a classic example of this would be like a battery. And batteries can go on for years also, depending on what kind of elements we're talking about in there. But anyhow, that's what we call a voltaic cell. Each of the voltaic cell that we have has redox reactions where you have electron transfers going on. And back from Gen Chem 1, you will remember that oxidation is the loss of electrons and reduction is gain of electrons. So then what we tend to do in a voltaic cell when we study these cells is we separate them into two half reactions. One half reaction is for the oxidation, the other one half reaction is for reduction then. So then what we do is we balance these reactions out, because in case of electrochemistry, when we talk about balancing equations, the balancing equations is not just to do with the coefficients, it actually has to do with balancing of electron transfer. Whatever number of electrons are given by one species should be accepted by the others, okay? And so there should be a total accountability of the gain and loss of electrons, and that's why the balancing of an equation in electrochemistry is a little bit different than what we do for stoichiometry. So we're going to learn that. Anyhow, one of the things that I just want to kind of give a little disclaimer, and you should also know because every textbook has this also, is that we know in our deepest of our heart, we know that if you have acidic condition, you will have what we call the hydronium ion in solution. But for the case of simplicity, we're going to write it as H plus ion. If we write H3O plus ion, then we actually have H2O as well as the H plus in there, which is how we get the hydronium ion. But we then have to start balancing oxygen and things like that. So to keep it simple, we just try to have H plus because we know that that's really what we're balancing. The other component in there is water, which also will be in the equation if we need it to be. So that's one of the disclaimers, and you will see what I'm talking about once we get to balancing the equations. So when we balance equations, by the way, just want to mention this a little bit, is the reaction can be an acidic or basic condition, depending on what we're doing. So we'll start with the acidic condition, we'll go on to the basic condition. So let's look at a redox equation. Here is a simple equation with iron 2 plus reacting with the nitrate ion to give iron 3 plus and nitrogen monoxide gas. Now it says here this is an acidic solution, and we have to know that so that we know how to balance an equation when the time comes. How do you also know it's an acidic solution? Maybe because you have nitrate ions over here, and nitrate ions can come from nitric acid. Nitrate ions can also come from sodium nitrate, but then you would have to show sodium ions over here, okay? And so, which is not shown over here. And sometimes they're not also, okay? But usually you would see those. The other thing that is not shown over here is, of course, water, which we will use later on for balancing the equation, but otherwise we know that water is ever present because of the aqueous conditions in this. So the first thing you have to do in a redox equation is realize what is getting oxidized and what is getting reduced. So oxidation here is of iron. Iron is going from 2 plus to 3 plus, and so therefore this is loss of electrons, and this loss of electrons, that is oxidation. So once you've established that iron is getting oxidized, and something else must be getting reduced. And the reduction over here is going on for nitrogen in the nitrate, not the entire nitrate, okay, but the nitrogen in the nitrate. So what you do then is you look at the oxidation number for nitrogen, which is going from +5 to +2 over here for nitrogen. How do we know it's +5 and +2? It's because of the oxygen. Oxygen is -2, and oxygen is pretty standard for us, okay? And so whenever you need to figure out the oxidation number of any element, you can definitely safely presume that oxygen is going to be -2. So if this is -2, this is a total of -6. And therefore, with the one negative charge over here, nitrogen is +5. So +5, and then -6 over here will give you a negative charge here. And then here nitrogen is going to be +2 because oxygen is -2. Okay, and so therefore nitrogen has to be +2. +5 to +2, that's a gain of electrons. So if there's a gain of electrons, then of course that is going to be reduction. Now here, let's just look at one more thing here before I move on forward, is that if you look at iron, iron is losing 1 electron, right? Iron is going from +2 to +3, so that's losing 1 electron. Nitrogen, on the other hand, is gaining 3 electrons, and that's what we talk about in balancing an equation. It's not just the fact that you have 1 nitrogen here and 1 nitrogen here. No, that's not the case. It's the fact that nitrogen will need 3 electrons, whereas iron is giving only 1 electron. So how many more irons would you need? So that's what we do when we start to balance these equations out, which we are going to do in a few minutes. But anyhow, it's important for us to know that this is an acidic condition, as I said before. All right, here are some of the steps that you would need for balancing a redox reaction in acidic conditions. We're going to do both conditions, acidic as well as basic. So the first one here is the acidic condition. And so it's a little bit of a process, but if you keep on track and if you keep stepwise, then things will be fine. So first of all, balance all other atoms other than hydrogen and oxygen. So for example, if you had nitrogens or iron, manganese, whatever it is, balance those out. Leave the hydrogen and oxygen for the last. Then you balance out oxygen by adding water on the opposite side. So whether it's the left side or the right side, it doesn't matter. You add water on the opposite side to balance out the oxygen. Once you balance out the oxygen, now you have to balance the hydrogen because you added water. So that's adding hydrogen there. So then you balance out the hydrogen using H plus again on the opposite side. Okay, because if one side you added the water, then the other side should add the hydronium ion, which again it's the H plus, the protons. Then what we have to do is balance the charges on both sides using electrons, because now you've added H plus. As it is, when you started doing the reaction, there were charges, just like we were seeing before in the previous equation where you had Fe2 plus to Fe3 plus. Things are already in ionic state. So if they are in ionic state, then you have to balance the charges such that charges on the left-hand side of the equation and right-hand side of the equation is the same. Okay, and so that is the most important part here. And then the next important part is multiply the entire oxidation reduction equation to have the same number of electrons. Okay, so once you have one of the equations balanced out, like the oxidation or the reduction, remember we're going to have to split the reaction into two. Okay, the redox. So the reduction is going on in one step and oxidation. You're balancing those two separately. So then you're going to multiply both of them such that both equations, such that both of them have the same number of electrons. That is our goal, okay, to make sure that we have the right number of transfer of electrons going on in there. And then we add up the redox reactions. At this point, the electrons should nullify. You should not see any electrons in the final reaction because you have made sure that the electron transfer was equal on both sides. Remember, one equation is reduction, one is oxidation. So one is losing electrons, one is gaining electrons. So electrons are on opposite sides for both equations. So they're going to cancel out. Okay, so once you add up the two redox reactions, you should have one equation with no electrons, but you may have water and hydrogen and H plus ions and all that. So let's look at this equation, okay, the one that I had before, which is iron 2 plus and the nitrate ion. And these are the oxidation states on the top, okay? So we know we're going from 2 plus to 3 plus. So here's the oxidation half reaction, which is very simple because iron is going from iron 2 plus to 3 plus and it's losing electrons. One word of warning, it's always a good idea to add electrons, whether you're adding it to the left side or the right side. Okay, do not subtract anything. When we write chemical equations, we don't subtract anything. All right, so do not subtract anything. So you might think that iron is giving 1 electron, so you can write iron 2 plus minus an electron. Do not do that. Okay, so just keep the electron plus side, wherever it is as a product or wherever it is as a reactant, use plus signs, no negatives, no subtractions in chemical equations. So iron 2 plus gives iron 3 plus plus 1 electron, okay, because it's losing only 1 electron. Then let's look at the reduction half equation. The reduction half reaction is the nitrate going to nitrogen monoxide. So that's how we start. So the first thing we have to do is balance the nitrogen. which luckily for us is already balanced out. So then we go ahead and balance the oxygen. And the way you balance the oxygen is by adding water. So we have 3 oxygens over here, and now we have a total of 3 oxygens here also. Okay, so you added 2 molecules of water on the right hand side. Now we are going to go ahead and balance the hydrogens by adding protons, but on the opposite side. So now we have 4H plus here, and you have 4 hydrogens over here. Do not worry about the charges, okay? Just look at the atoms, that's it. Don't worry about the charges because it's going to come. Our next steps are going to be to balance out the charge, okay? Right now we're just focusing on atoms. Okay, so then we have to balance the electrons, okay? So now we do this. So we have 4H plus over here, we have a negative over here, we have no charges over here, which means this is total 0, which means that whatever charges we have to balance, everything has to balance out over here, which means that the total here should be 0. Here it is already 0. There are no charges on the right hand side. So on the left hand side, you have to add 3 electrons. So 3 negative plus 1 negative, that is 4 negative, and then the 4 hydrogen plus, so 4 plus over here, that gives you a total of 0 charge. So that is how you balance out the charges. Now, if there was a charge left over on the right hand side, if there was a negative 1, then you want to make sure that both sides have negative 1s, okay, on them. Okay, so you can guess where we're going next, because here you have 3 electrons that you added on the left hand side. Now remember, this is a reduction half reaction. If this is a reduction half reaction, in reduction we call it gain of electrons. So the electrons are being gained, and that's why they're on the left hand side of the equation. In oxidation, electrons are given. So if they're given, they're going to be on the right hand side of the equation. And that's how we get electrons on the opposite sides of the equation. And so yes, now you know where we're going. We have to balance out our electrons. So when you combine the two equations, we're going to have to multiply this equation by 3 in order to get the 3 electrons that we need over here. So, or 3 electrons that we need from iron in order to have the 3 electrons that nitrogen needs. So, which means that this equation, the oxidation has to be multiplied by 3, which we did over here. So now we have 3 electrons here, and we have 3 electrons here. It's really important to balance the electrons. Don't worry about anything else. And then here we have the other equation, which is already balanced out as far as electrons and everything is concerned. And then we go ahead and cancel out our electrons, which should be on the opposite side, and then just add up everything. Okay, so you have the 4 protons, the iron 2 plus, and everything. So this is the stoichiometric equation now that we have. This would have been very hard for you to get without doing it this way, without doing it electronically. All right, so for redox equations, you have to do these equations electronically. Now let's look at how to balance a redox equation in base. So in bases, you should have hydroxides remaining. Okay, water is ever present everywhere, but in a basic condition, you should not have any protons. So when you start balancing the equation in a basic condition, everything is going to be the same as you have for the acidic condition, no problem, which means you balance the oxygen using water, then you balance the hydrogen using the proton. Once you add the proton, that's when you have to add hydroxide to both sides in order to balance out the protons. Okay, when you have the hydrogen ion and the hydroxide ion on both sides, then you combine them to form water, and then you'll have to cancel out the water molecules. And if you're thinking it's going to cause an imbalance in your water, well, we'll find out. Okay, because hopefully it should not. Okay, so let's look at this equation, which is going to be now our example for balancing an equation in basic conditions. So here is our equation. You can read all of this yourself. That iron yields plumbite ion in basic solution, and the hypochlorite solution is turning it to lead oxide. So it's all right here. Okay, this is the equation that we need, but we need to balance this using a basic condition. All right, so the first thing that we have to do is figure out the numbers, the oxidation numbers for everything. So here we start with lead and chlorine, okay, because those are the ones that are changing. Remember, oxygen will not change, okay, and usually hydrogen also you don't consider as far as the redox equation is concerned, unless you see a hydrogen going to hydride or something like that. And here, don't panic that you don't see any hydrogen on the right hand side, because remember, we're going to balance the equation. So we're going to get water and all that good stuff. So here is lead, and lead is going from +2 to +4. So which means this is getting oxidized. Chlorine is going from -1, so excuse me, from +1 to -1. So which means that this is gaining electrons, and so this is getting reduced. So lead is getting oxidized, chlorine is getting reduced over here. And how do we know this is a +1? Because oxygen is -2 and there's a -1 left over, so chlorine must be +1. So then once we know all of this, then we can actually separate the equation out into two portions, right? The reduction and the oxidation. So let's go on. So we're going to break down the equation into two redox equations, the oxidation and the reduction. So let's look at the oxidation first. So we balance out the lead and the oxygen. So lead here is going from lead hydroxide ion to lead oxide, and so lead is already balanced out. Oxygen, we have 2 here and 3 here, so we need to add 1 molecule of water, okay, to balance out the oxygen. Then you balance the hydrogen. There are 3 hydrogens over here. We added 2 for the water, and so we had to add 1 more H plus in order to balance out the hydrogen. So now we have 3 hydrogens here, and pretty much everything is balanced out now. Now we just need to balance out the electrons. So we have 1 negative over here, so we want to make sure that you have a total of 1 negative here as well. So you had the 1 hydrogen ion, which is 1 positive. So you need to add 2 electrons here in order to make it 1 negative. So 1 plus 2 negative gives you 1 negative. So this is oxidation, remember, and when you're doing oxidation, electrons should be part of your product. In reduction, it will be part of your reactant. So our oxidation is all balanced out. Let's look at the reduction equations now. So here's the chlorine. Now the chlorine also had the oxygen in it, okay, so which means that we need to do the whole process again, unlike what we had before with iron. We lucked out in that case, there was no oxygen. So here we have oxygen here, so which means we need to add 1 molecule of water. Chlorine is balanced out, okay, so once you added water here to balance the hydrogen, you add 2 protons on the left hand side. And then finally, we're going to balance the electrons. So you have 2 positive, 1 negative, total of 1 positive over here. And then you have 1 negative here also. So whatever you do, then you have to have more negative here because this is 1 negative. So you should have a leftover of 1 negative here. So which means if you add 2 electrons here, you balance out the 2 plus over here. So you're left with that 1 negative. Also, this is reduction, which means you have to actually gain electrons. So which means it should be on the left hand side. Then you can see that we have 2 electrons here and 2 electrons here, which means that our electrons are all balanced out. Okay, very nice. Otherwise, we would be multiplying equations at this point to make sure that the electrons are balanced out. But they are already all balanced out. So we lucked out in another way. So then once everything is all balanced out, then we will combine the half reactions. And so copy everything down word to word. Okay, don't forget any atom at all. And then once you write them out, then go ahead and cancel out your electrons, which should be equal at this point. And if there's anything extra also, then you cancel it out. So for example, here we have the proton over here on the right hand side and 2 protons over here on the left hand side. So you got to cross those out and make sure that you have the excess remaining. So here it was 2 protons, so which means 1 is remaining here. There will be no protons left on the right hand side. Okay, and so this becomes your final equation, and again remember, no electrons on this one. So far we have not done anything new. We've just taken the reaction and we balanced it out using the acidic method. Now to convert it to a basic solution, we're going to add hydroxide ions to each side. And this is why you don't have to worry about the electrons, because once you add the hydroxide, it's going to go ahead and convert the H plus to water. There's an acid-base reaction that goes on and you get water, so which means that you don't have to worry about electrons anymore. So the important thing is that you add it to both sides, okay? And how many hydroxides do you add? Well, it depends on how many protons you have. So here we have only one proton, so we're going to add only one hydroxide, but you got to add it to both sides. Okay, you just can't add it to one side. So add it to both sides over here. Okay, now on the left hand side, you have the hydroxide and the H plus. That gives you the water, all right, on this side. So now you have this equation, which is your final equation, almost there, not final, I should say penultimate. And so here is the water here, the rest of the equation is the same, and then you have the hydroxide here. To come to the final equation, you have to cancel out the water, because before we had to add water to our equations, and now we have water on the left hand side and the right hand side. So you need to cross out the waters, okay, over here, and then once you cross out the extra waters that you will have the excess remaining. Here in this case it will be on the right hand side. So you have one water molecule on the left, so you have only one water molecule left on the right hand side. So this is our final equation, and you see that there are no H pluses here, there are no protons, because this is a basic condition. So in this case you can have water, but then you have to have hydroxides in there in order to show that this is actually a basic condition balancing. So you can see that the entire reaction was balanced the same way as it was in the acidic condition. The only thing you have to do at the end is add hydroxide. So very simple to do. And that's pretty much it for this little portion of electrochemistry. So you just need to learn how to balance the redox equations, okay, in both acidic and basic mediums.